Hey there, Algebra 2. Hope you enjoyed that quiz. The next section that we need to talk about is how do we solve exponential and logarithmic equations and inequalities, and then inequalities as well. We'll touch a little bit on that, but those are the same rules that apply. So this is section 4.5 out of your notes, and what you should do is just write down your assignment right now. I want you to do problems 21 to 36. And a lot of it is just practicing those rules associated with raising things to powers and whatnot. The most important thing, though, that you're going to do, from my experience working in finance, is using logs to find powers, to solve for powers. Okay, so what we're talking about are exponential equations. And the idea is, hey, if we can get the same base, okay, on both sides, then it's just a matter of setting x equal to y. Well, and the other way to do that, which I've seen much more common, is if you've got two different expressions and you've got something raised to a power here, then the way to bring that power down so you can solve for it is by taking the log of both sides. And that's really just the best way to go, and I'll show you some examples here. So on this problem here, it says solve and check. Well, in this example, of course, 9 and 27 have something in common. They're both 3 raised to a power. Well, so if we rewrite these expressions, you can see that this is really 3 to the power 2, right, raised to the power 8 minus x, and of course 27 is 3 to the third, and that is being raised to the power x minus 3. Of course, the rules then is multiply the exponents. When you raise a power to a power, you multiply the exponents. And that means distributing the 2 to both the 8 and the negative x, and in this case, the 3 to both the x and the negative 3. Well, now you're saying, hey, 3 to something equals 3 to something. Those two somethings have to be the same, and that's, you can basically, the problem is no longer exponential. It just drops down to a lower case situation. So the bases are the same, so therefore the exponents are equal, and then that's really easy to solve for. As far as checking that, you simply need to plug that back into the expression here and make sure it evaluates out correctly. Let's try another problem here. See if you can do this ahead of me. All right, now you're thinking, well, 4 raised to something, 5 raised to something, ugh, I don't like that one at all. Well, this is a classic case of wanting to take the log of both sides. Because when you take the log of something raised to a power, that power comes out front. And that's what's so helpful. And again, that's the power property, right? So now you've got x minus 1 times the log of 4 equals the log of 5. And now simply divide both sides by the log of 4. And x minus 1 equals the log of 5 over the log of 4. And of course, base is 10, so it's easy to do on your calculator. And then you're going to add 1 to both sides. And when you calculate that out, you do get roughly 2.16. And use this, you can do this on your calculator, and of course, you're going to have to do the logs on your calculator anyways. So, hope that is clear. You're going to use this process a lot more in those scenarios where how many years does it take to reach a certain dollar amount or a certain population. By taking the log of an expression, you're able to pull the power out in front of the expression and then solve for it using this process. Please star this in your notes. I'm sure we'll do some more problems like this in class. Of course, so here's an example that kind of ties right to that. Suppose a culture doubles in size every hour. How many hours will it take for the number of bacteria to exceed 1 million? There's more than one way to do this problem. How the book shows you isn't necessarily how I would do it, but that's okay. I'm just going to follow that example right now. So at 0 hours, there's 1 bacteria, or 2 to the 0. At 1 hour, there's 2 bacteria, 2 to the first. And so you can see here that this expression should be 2 to the number of hours, or n is the number of hours. Well, when will that exceed 1 million? Now what they do is write 1 million in scientific notation, and there is a really good reason for why they do that. But if you just kept this as a million and then use the power of logs property, you're going to get the same answer. All right, so here it is. Now they're saying the log of both of these, of course, it's going to bring the n out front. So log 10 of 2 equals log 10 of 10 to the 6th. The reason they like doing this part, let me move my picture out of the way. The reason they like doing this part is because you'll notice log 10 of 10 is just 1, right? And that's why that power 6 comes out front. And that's what they're trying to show you right in this step here. The 6 is going to go out front, the n is going to go out front. Watch, wait for it, right? Log base 10 of 10 to the 6th is just 6. So now we've got a much simpler expression to solve for. Let me keep scrolling down. So that means n has to be greater than 6 over the log of 2, and you can evaluate that on a calculator. So it says n has got to be greater than 19.94, and of course we're talking 20 years. Now when you check this, make sure you plug it in, and you'll see indeed that after 20 hours the bacteria exceeds 1 million. One more example here, talking about tripling things. So you receive 1 penny on the first day, and then triple that on the second day, and so on for a month. The question is, when do you receive $1 million? So see if you can solve this problem just like we did in the last example, where you write 1 million in scientific notation. All right, you're back. Here you go. This is what it looks like. So you should be starting out with 3 to the n minus 1, because you're tripling this in every single scenario. So that's a really nice formula. So 3 to the n minus 1, right? Because on the first day, you've got 1 cent. So 1 minus 1 is 0. 3 to the 0 is 1 cent. But then after that, it keeps tripling. And boy, do things go really fast when you triple values. Okay, so we've written it in scientific notation. Of course, now we're going to take the log of both sides, and you should be jumping out of your seat saying, Mr. Rising, I got it. This isn't so bad, right? Because that n minus 1 comes out front. Of course, this 8 is going to come out front, right? Here's my power of logarithms. That's what it really looks like, because log base 10 of 10, right, is just this power raised to a power. Now divide 8 by the log of 3 on a calculator, and lo and behold, you're going to love this. This is actually just the most amazing thing ever. Of course, I'm going to add 1 to both sides, and evaluating that, when the number of days exceeds 17.8, you're going to have more than $1 million. And it's like, that's absolutely ridiculous that only 18 days after starting with a penny and tripling it, you have more than $1 million. But that is the power of compounding. I think at this point, rather than saying, hey, keep going, it's really your choice, but I would do problems 21 to 27, because I just gave you some examples, and you really need to have those properties in front of you so you can manipulate the problems. When you finish that, come back, or if you have connectivity issues at home and you want to continue the lecture, let's go. So with logarithmic equations, again, that's when you have logarithmic expressions that contain a variable, right? So here, the log b of x equals the log b of y. Well, in that case, x has got to equal y. Seems to make a lot of sense. You're going to see a little trick here that they're going to use over and over, and it's a really cool trick. So let's do some examples here. Log 6 of 2x minus 1 equals negative 1. Well, where do we even start to solve this? Well, the solution is raise both sides, or basically give both sides the power 6 and raise them to the equation. So what we're saying is, because this base is 6, let's raise both things, both sides to the 6 to some base, for lack of better terms. Now you can easily evaluate this. 6 to the negative first is just 1/6. And can you evaluate this? Right, the rule is anytime you have a base raised to a log with the same base, then it's just that result. And that's what you're going to see right there. Now this is a really easy problem to solve, and you can simplify it out. So this is the trick that we're going to use for the remainder here of raising things to the same base. And I'll show you how this plays out. So in this one here, before you raise anything to the same base, you need to simplify. When we subtract logs of the same base, that means divide, right? So this is 100 divided by x plus 1, and that of course goes inside the log to the fourth. Now let's raise both sides. I keep saying raise, but really saying let's make 4 as the base of both sides, right? That really simplifies it. And now you just got 100 over x plus 1 equals 4. And now you're like, oh wait, this is just easy algebra. No big deal. I got a couple more examples here, and I want to just walk you through them. On this one, where should we start? Well, whenever you have a log and the result is raised to the power, that power comes out front. Right off the bat, straight off the bat, that power comes right off the front. And that's the power property. Well, then divide both sides by that 4. So now you got log 5, base 5 of x equals 2. Now everything's nice and simple. Well, when you get down to this expression, I hope you can just rewrite it, right? Base is 5, result I don't know, and the power is 2. Well, that's just 5 to the second. Wait a minute, 5 to the second? 25. Last example I want to look at is, now here we're adding 2 logs with the same base. So again, when you add things, you need to multiply them. So I can rewrite this as log base 12 of x times x plus 1 to the first. Now let's rewrite that with a base of 12 on both sides. Right? And again, the reason we want to do that is it brings this whole expression right in here out front and becomes the whole real deal. Right? So now you've got a quadratic. And if you guys can't solve quadratics by now, oh man, you're in big trouble. Okay? It is important though to check these results because you want to make sure that you get a working solution. The reason we need to check the solutions is you can see here that x is equal to 3 or x is equal to negative 4. Well, 3 is a working solution, but 4 is undefined because you can't get a result that is negative from raising something to a power. All right, so let me just say that again. When you take 12 to any power, you're not going to get a negative 4. So again, just to review, I just had a phone call. My family arrived. Grace, Coral, and Ashley are still working in the back. Here, you want to say hi to everybody? Hi. See, there's the kids. The girls working in the back. Look, they're getting snacks. See, this is what happens when you come and work after school and work hard. You get snacks and all that good stuff. Okay, so just a quick reminder. 12 to, there's no such power that you can raise 12 to get negative 4. And that's why this here is undefined. And that's what this caution says, is just like, hey, watch out for values, solutions, that are not solutions in the original equation, right? They might mathematically be there, but not in practicality. The last thing you need to do, and there's some problems at the very end, is they want you to use a table and a graph to solve inequalities or equalities. And what this means is being able to use the calculator. So what they want you to do is enter the 2 to the x plus 1 as y1 and the 8192 as y2. And you can either compare those values, so where is y1 greater than y2, or you can also do it graphically. And then of course that means your solution set is of x is that x's are greater than 16. So please finish those problems 28 through 36. It'd be better to have a graphing calculator on 34 through 36. So if you want to do those problems now, you can. And if you have any questions, let me know how we can help.